Sirup was not here in the beginning of the last talk, so I planned on cracking a joke, but now he's here, so I can't do that. Okay. So, no, but it doesn't make sense since he's here. I was planning to crack a joke of that. Probably he's sleeping, gone back to his TIFR routines. Anyway, so my talk will be more on the observational side of dark energy, and although it will have a lot of overlap with which Anjan has said in the previous talk, so there will be figures which are the same. Excuse me for that, but we'll try to see if we can get a little more. And of course, Anjan has done all the theoretical stuff, so I will not go into theory. So this basically slide is basically after sort of a extension of a discussion that we had on the first day when John was giving his first Chandrasekhar lecture, and at the end there was this question whether we want to build bigger machines when we don't know theory, and the idea was that in the absence of theory, we should probably be led by data. And I think for dark energy, this is very, very true. We don't know really what is dark energy. We don't have a convincing theory. So what we have to do is that we have to be led by data. And so this data is our candles in the darkness. Okay? Now, as Anjan said, dark energy manifests itself in the expansion of the universe and the growth of structures. And the candles, the rulers, the clumps, the sirens, whatever I wrote in the title, these are the probes that looks at the expansion and the growth of structures, as Anjan already showed. And I'm going to go through each of them, and very little through this. Initially, of course, I thought I will just talk about candles, ruler, and clumps, but then this being ICTS, I couldn't resist the temptation of adding sirens, because now that gravitational waves have been detected, that becomes another probe of dark energy, of course, in the very, very far future. I'm not going to talk about it at all, just I'm going to mention it. So if you look at the different dark energy probes, you have the ones that I mentioned, the standard candles. I'll mention why I mean standard candles. Something which is called standard rulers. Then we'll have standard sirens. And then, of course, I cannot say standard clumps, but they're clump statistics. And these come in different ways we can probe the universe. For example, we can have supernovae, which will fall under the standard candle. We can have the baryonic acoustic oscillations, so the CMB peaks. These will come under the standard rulers. We'll have the lensing and the clusters, which will come in the clump statistics. Or we can have standard sirens, which comes from gamma ray burst. And then there is a huge number of others, which is, for example, the ISW effect, redshift distortions. I'm not going to go to any one of those. Galaxy ages, time delays. In the future, one may even do something very, very interesting where one may try to probe the expansion of the universe exactly through the change in the redshift of objects. So basically, we look at the same object now and 5 years later, and if the redshift changes, and if we are good enough, the instrument is good enough to differentiate between this redshift, that's due to the expansion of the universe. So that's probably will be possible, and there's one of the themes that one can do with the 30-meter telescope that India is part of. So this is a question which Surya was asking. Where is dark energy important, and what kind of probes we need? So as you see, all the probes that we have written in the last slide, these sort of span the redshift from 0 to up to a redshift of 3, except the CMB, which sort of gives you an integrated number from 0 to the last scattering. Okay. So all the other redshifts are probed by these different probes. For example, supernova, we go up to redshift of 2 to 3. There's this Lyman alpha forest, which is slightly larger actually. So you can go up to redshift of 6 or 7. Then there's this clumps, the cluster abundance, the lensing, galaxy surveys. And this is because if you look at dark energy and ask the question where dark energy becomes important, we can think of just like the matter radiation equality, we can think of a matter dark energy equality. And the typical number is around redshift of 0.7 or so. That's where matter and dark energy is more or less equal. And so a little bit before to us is the range where we want to probe dark energy. So I'll not talk about it at all, it's good. So Arnav has already showed it. Everything given from the Friedman equation, the expansion, and we can talk about different lengths, angles, and stuff like that. And of course, we can also look at the growth of structures. What he did not mention, and I think I should stress on this thing, is that if you look at length scales or sizes or angles, and which are basically looks at the expansion of the universe, the background expansion, and the growth of structures, which looks at how the perturbations grow, then these two are very complementary to each other. In the sense, suppose it is not dark energy, it is some kind of modification of gravity, then this probe and the solution of this probe will not agree with each other. And so you need to have probes of the expansion as well as probe of growth together so that we know that it is actually something like dark energy and not something which is due to a change in gravity. And in fact, all the anomalies that Anjan talked about are at late universe objects, and this is where this growth of structures become important. So that's something that one should keep in mind. So let's start with candles. So what's a candle? A candle is something which has a luminosity L, and we have a flux, which you receive at a distance d, and so the flux and the luminosity is simply related by 4 pi d squared. If the candle was over here, this d would be the distance between us and the candle. In cosmology, this is slightly different. It is the luminosity distance, which depends on the cosmological parameters. So if you have a standardized candle, then the further we go, we see the candle fainter and fainter, and how faint it is depends on how much is the distance. So if you can have the same candle at different redshifts, then we know what is the distance to that candle at different redshifts. And so if I know the redshift of this candle, then I can plot the distance to the redshift. And that's what supernova cosmology does. And the idea is that in a series of papers, these people who ultimately got the Nobel Prize showed that this type 1 supernovae can be used as standard candles. It was not obvious that you can use standard candles, but we showed that this can be used as standard candles. And the reason it is used as standard candles is that type 1 supernovae, the luminosity is basically happens when the mass transferred goes above the Chandrasekhar limit, and that's a particular number. So it's like a critical mass, and so it's a critical energy that's sort of. And what these people showed that if you look at the luminosity and the rate of decline, these are correlated. So different supernovae have a different luminosity and rate of decline. All of them can be brought together, and you can use it as standardized candle. And so this is what it is. Different supernovas can all be put in a simple luminosity plot, and this peak and this decline is correlated. Okay. So one does this thing of looking at the standard candle as farther and farther and finding the distance from the flux. And when you do that, when you look at the magnitude, so the actual magnitude minus the apparent magnitude, and you plot it, this is what got them the Nobel Prize, you see that this data is fit by a cosmological model which needs a non-zero dark energy. So omega lambda, the fit over there that was simple was omega lambda 0.70% dark energy. So there is more data which is above the omega lambda equal to 0 line. So you need these objects to be farther away than if there was no dark energy. So the expansion is pushing things farther away. So that told us that there is a need of an expansion, an extra expansion, and that extra expansion basically came from dark energy. Okay. Now, of course, we have much more data. This is also a little dated. It's like 7, 8 years old. There are more data over here, and through it, we can have a very, very precise measurement of the expansion history of the universe, and all says that there has to be a dark energy. Now, one can, of course, add CMB to the candles, which is the first thing one does. So Anjan has already told about this. These are the CMB dark and gold spots. You do the statistics of it. You get the CMB power spectrum. And if you look at the height over here, then this peak is theoretically given. You observe the peak in the statistics, so we know what is the ratio of the theoretical height to the observed peak length scale, and the ratio gives us the distance to the CMB. And from that peak position, one can sort of say that there needs to be a dark energy. Of course, this is an integrated effect over all the redshift from 0 to 1,000. So it's not very good by itself to give very strong constraint to dark energy, but it does So one can add the CMB with this, and this is just pre-Planck, because I'm going to go post-Planck, what we knew about dark energy. So supernova gave you this kind of contours, the CMB gave you this kind of contours, and then you see, if you add both of them, forget about the BO at present, you need a universe which has 70% dark energy. Okay, and this is what it is. And this has not changed much. So there is a conclusive evidence that there is dark energy. And of course, with the CMB and the supernova, we also knew that if you look at the evolution of the different components, then at 3,100 years after Big Bang, so when the CMB started, over there is absolutely no dark energy. It's dominated by dark matter, but now it's dominated by dark energy. So dark energy is absolutely relatively new. Okay. Next, we go to rulers. So after the candles, let's talk about rulers. So I showed this picture, and we have seen this picture. This tells us the fluctuation in the photon. But at the time of decoupling, just before decoupling, this fluctuation in the photon was also coupled to fluctuation in matter. So just like the fluctuation, this is in CL space, this is in delta R, so this is basically the RMS fluctuation. Just like an RMS fluctuation photons, at the same epoch of decoupling, I can have an RMS fluctuation in matter, and these two are coupled. This is the fluctuation together of these two that gives you the CMB. And so there is fluctuation in matter. So the matter itself, our spectrum has oscillations. And this is the matter fluctuations that will grow into galaxies and clusters of galaxies in the later universe. And so it grows, structures grow. And if I try to recover this fluctuation in the power spectrum at later universe, then if there is baryons, then the power spectrum should have fluctuations like this. And in fact, this is what we see. So if I look at the power spectrum from galaxies, it also has fluctuations, just like the fluctuations in CMB. Of course, the fluctuations are very difficult because it depends on the ratio of baryons to dark matter, and the baryon to dark matter ratio is 20%, so the fluctuation is like 1/5 times. So if we can look at these fluctuations, look at these peaks, then just like the CMB, we can look at the peak position, and that gives us the expansion history of the universe. And this is exactly what is done. So think of what is happening in the early universe. Suppose the early universe was a photon baryon dark matter bath, and there is a perturbation. The perturbation grows. This starts, when it starts at Big Bang in some sense. Okay? It grows and it stops at the decoupling. So at the decoupling, there's an excess matter. And so this will give a sort of excess ring of galaxy around the center. And so this is the distance that is imprinted in the matter power spectrum, in the power spectrum of galaxies. Let's not go through this. So what will happen is that in reality, of course, there is not one thing. It's a random fluctuation. It's a random Gaussian distribution. And so all these circles will overlap, will interfere with each other, and the resultant fluctuation will be embedded in the matter distribution. So if you look at the statistics to the Fourier transform of the matter distribution, the scale, whatever that was, this size will be taken out. And this is exactly what people have done. So if you look at the statistics of galaxies, one would expect this size, and this is 105 H inverse co-moving megaparsec, this size to be imprinted in the distribution of galaxies. So at exactly this size, there will be an excess of galaxies. So you look at galaxy all around the universe, and we'll see that there's an excess. This is of course theory, and this was the very famous result when the first detection. As you can see, there is an excess. This is from SDSS. There is an excess over here. You can change your omega matter. As Anjan said, things are very different when omega matter changes, but as you can see, the peak over here still remains approximately at 105 megaparsec. This is a co-moving distance. So if you find the same distance at different redshifts with different distribution of galaxies, we can use it to see how the universe expands, because the real distance depends how the universe expands and multiplied by the co-moving distance.
Sorry, this is relative to the peak.
No, so
So what
not important. As I said, initially it was all it's just a scale that's printed, so it's everywhere. Think of raindrops falling on the thing, and every raindrop will give you a wake. And if I take a snapshot for 5 minutes, you will not see it, but if you do the statistics of it, that size will come. That's exactly what's happening. In fact, now we can see this at different redshifts. So there is this bump, which is this famous experiment, the Wigglez, at the low redshift, so from 0.2 to 0.6 galaxies, then 0.4 to 0.8, 0.6 to 1, 0.2 to... So in every redshift bin, you have a co-moving. Now this is a co-moving size, which basically means the physical size is different, and so I know a ruler, so this co-moving size is the ruler, and so the ruler gets different physical sizes, and so the angular diameter distance is different at different redshifts, and that's how we have got the Hubble diagram. In fact, if you look over here, so forget about this plot. If you look over here, this was the supernova redshift diagram, which gives you the expansion of the universe, but I can now plot the standard ruler on top of the supernova redshift diagram. So now I'm looking at the expansion of the universe, not only with supernovae, but also with the baryonic acoustic oscillations. And the cute thing and the very nice thing is that the candles and the rulers, they both agree. They both come over here. Let's now go to clumps. When I talk about clumps, we can do a lot of things with clumps. So this is not about the general expansion of the universe. It is about how the perturbations in the universe grow, how matter grows. So this is the second part, the dynamical part. And you can use clumps by counting them. You can use clumps as rulers, actually, very interestingly. You can do lensing with clumps, and let me show. So this is sort of to give an idea if there's a universe in matter at very early times, and this is what structures and collapses and grows together gravitationally, and ultimately becomes a universe which you know which is nearby. And over here, everything that is not dark is matter. So there are filaments, which is basically think of small, tiny clumps. And then there are regions in space where the clumps are very strong. These are super clumps. So these are basically galaxies. And then you can think of, these are basically clusters of galaxies, and then you can think of a few of them as supercluster of galaxies. So, of course, we cannot see. These are made of dark matter, so if there is some tracers which can sort of point this out, we can pick this up. And what we can do is that we can do statistics of this. We can count these. We can do lensing of light through this. And so these dark clumps again become a probe of the universe. Because ultimately, remember, the way it went from this stage at early universe to this stage at late universe depends on how the universe expanded, and the expansion history is embedded in it. And so the statistics counts everything depends on the expansion history, and so it depends on the dark energy. Okay. Now if I can zoom in over here to look at one of the clumps, this would look like this. This is a cluster of galaxy, and so we can sort of identify a cluster of galaxy in the real world, and we can count them. Of course, these are dark matter, and these are big objects, but in real world, dark matters are difficult, so we have to sort of somehow see it through either X-rays or in the CMB or in galaxy distributions. But before we start counting clumps, we can do something very interesting. We can actually try to use the clumps itself as rulers. Remember, the rulers previously were standard rulers, which was from CMB or the BAO. But now, if we can identify these clumps, we can use those clumps as rulers. So think of something like this. You have a survey, which is in X-ray, and you have a survey which is in CMB, which is called SZ. It's due to Compton distortion, inverse Compton distortion of the photons. There is a signature. And then you sort of pick up the same clumps in both SZ and X-ray. And if you can do that, then it turns out by a very simple idea that the way the CMB emission comes is proportional to some multiplication of the density of the gas, the temperature, and the length scale of the clump. And how the X-ray goes is a different combination of the length scale. One can actually calculate this length scale from just these two emissions. And so if you just identify the clumps, you can do that if you have observed in both and calculate the length scale. And now, instead of supernova and BAO, you can have the same kind of the angular diameter distance, the expansion history of the universe from clumps, from structures. Okay. And it turns out that you can constrain W, or basically dark energy, very well by that. This is something. The X-ray has. X-ray, you have all of these, you need, yeah. You need to follow-up observations to know the redshifts. For all of this, so even for supernova, you need to have a follow-up observation to know the redshifts. So all dark energy surveys, you need follow-up observation, and this is where the sirens are very good. But over there also the follow-up observation. Okay. Yeah, numbers are not visible. Yeah, it's there. Cross is at the correct point. Yes, cross is at the correct point. Yes, yeah, at the correct point. Now this is of course needs more statistics, and there is this very large survey which is going up next year called the Eurocita survey, which is going to all sky and got thousands and hundreds of thousands of clumps, and with which you can do this. Okay. But then, other than doing a ruler with the clumps, we can actually use the clumps to do counting of clumps. And why is that very important? Because it turns out, if I look at the counts of clumps, and counts basically means if I count the number of clumps of a certain mass in a certain redshift range, so take a mass bin and take a redshift bin, it turns out, if you look at this thing, that is what is the number of objects a certain mass, the function of mass, these have an universal relation. So this is very, once we know the cosmology, once we know how the universe has evolved, we know exactly what to expect of the number of counts of objects. Okay. And this is universal at every redshift. This is basically simulations and physics. And so if we can count, again, as I said, because the numbers will depend on how the universe expanded, then from this number counts, we can say how the universe has expanded. In fact, for example, if we look at cosmology with clusters, which are clumps, as you can see, if you have different kinds of 3 different W's, which Anjan said is the equation of state, you can see that they are very, very different. So if you can differentiate between this and this, you know how to do it, how to get it. Okay. In the future, as I said, there is this survey called Eurocita. With Eurocita, we can do something very, very interesting. So one of the first time when people talked about using supernova and the CMB to do dark energy, they came up with this idea of cosmic complementarity. And this is because, as you can see, the degeneracy directions between omega matter and dark energy is orthogonal for supernova and the CMB. Okay. And so if you add this two, you get very strong constraint. It turns out, if you go in the future with clusters, so not supernova, but now with CMB and clump clouds, you again have very strong orthogonal directions. So this is from counting clumps, and this is from CMB. And so you get very strong. So again, it's a new age of cosmic complementarity you can have. Okay, when there are clumps, you can do lensing. So here's an example of lensing in real life. This is a lensing of a wine glass. Through a wine glass, if you have a candle, and you have a wine glass, you can put the candle beside the wine glass, and depending on where your candle is with respect to the center of the wine glass, you can have, so this candle is over here, you can have different lensing patterns. So you can have a complete rings, you can have arcs and stuff like that. And if the candle is very far away, then you'll have very, very tiny lensing, and that is weak lensing. In fact, if you look at the universe, this is the universe that we live in, and if you look at the universe, if suppose this is the universe, this is a large distance in the universe, at higher and higher distance, and there are some background galaxies. And let's say for simplicity, these background galaxies are circular, which they are not, but let's say. Then the lensing will distort the shape of the galaxies, and we will observe elliptical galaxies. The thing is that if you look at all these ellipticities are not random. They are correlated. And so if you look at the correlation of these ellipticities, so you look at the shear statistics, then from the shear statistics, one can know how much mass is over here. And that, again, depends on how the universe has grown. And so how the universe has grown gives you the correlation of these ellipticities of the background galaxies. And so that, again, goes back and does dark energy. So there's another way the clumps will come. So if we combine all of these, then where do we stand now? We come at a place where you can say that the lambda CDM triumphs. So this is what Anjan showed. This is the very beautiful plot out of Planck. You can see the CMB data points, and the 6-parameter lambda CDM fits very, very well. You can see this is the deviation. So there is a 10% from the best fit. That's how those. If you look at large-scale structure, so this is the angular diameter distance. Again, lambda CDM fits very well. This is the deviation. So everything is accurate to 5 to 6%. So this is sort of saying that, okay, the lambda CDM, where dark energy is constant, is a very, very good description of a universe. In fact, if you look at it, then you know dark energy to this accuracy. However, one must remember that in this 6-parameter lambda CDM model, the accuracy of finding omega matter determines the accuracy of finding your dark energy, because you have assumed the universe to be flat. So there's no curvature. So how accurately you determine omega matter is exactly the accuracy that you determine dark energy. Now, it is true that the universe is flat, almost, we think, but even if you change it a little bit, these things will change and we may move away from lambda CDM. So if you look at this plot, this is putting everything together. This is the power spectrum over many, many different scales. So from the largest scales to the smallest scales. This region is from the CMB, so red is CMB, the large scales, and this region is from structure formation coming from weak-lensing. These are small scales, and this line is the best fit lambda CDM model to Planck. As you can see, it's a very good representation of the entire range, and that's why I say the lambda CDM is a good theory to manage the entire range. However, if you look a little carefully, and this is where I will go Anjan's way, over here, as you can see, the large-scale structure observation, or the growth of structure observation, predicts a slightly less power than what you would expect from CMB. And this is the cause of all the discrepancies that Anjan talked about, and I'm going to speak about again. So it looks like this. These scales are linear, non-linear is over here. Yeah. So even in linear scale, there's discrepancy. Yeah. It's not only non-linear. And so it looks like when you look at large-scale structure power, the power is a little less than what is from the CMB. And we don't know why it is, and that may sort of give us an idea that maybe there is some hints of beyond lambda CDM. Of course, this is very little, but everything starts little, and so we should not just completely ignore it. Okay. Now, with lambda, we did pretty well, but when you talk about it's finding it's hard. So if you want to change whether it is lambda or not, so you want to look at difference between W of -1 and something which is not -1. Why is it very difficult? Why can't we do it right away? It turns out that it's very hard, and to give you quickly, I will show you how hard it is. So over here, just look at the black line, which is the lambda CDM, and the brown and the green line, which is where W is changed by 10%. And this is the general expansion history of the universe as a function of redshift. As you can see, if you change W by 10%, which is slightly different from lambda CDM, the history most of the time changes by less than 5%. There's a few percent change in the history of the universe. So you have to have probes which is accurate enough to differentiate a 1% change in the expansion history of the universe over a large range so that we can differentiate W of -1 with something which is not -1. We do not expect W to be very different from -1. So that's very important. We can think of growth, which is again the other thing, which is not the expansion, but the growth of structures. Even over here, if you look at the green line, and it's like a 1% change over the entire history of the universe. So even in the growth, we need to differentiate 1% change over the entire history of the universe. Of course, this adds up in chi-squared. Okay. So we are looking at changes which are 1% to 2% in the fundamental expansion and the growth of structures, and that will probe a deviation of lambda CDM. This is why it is so hard to do. If you look at, for example, the angular diameter distance, again, as you can see, a 5% change is what you get nearby. You can think of the CMB. It's almost impossible to differentiate different W models in CMB because this is the error bar, the cosmic variance in CMB, all inside. Okay. You can look at the galaxies, power spectrum, large-scale structure. So this 2% change is the kind of thing we're looking at. So we have to have power spectrum of galaxies, a power spectrum of the large-scale structure at the 2% accuracy if you want to probe lambda CDM to beyond lambda CDM. The thing is that we are close to it right now. we are approaching, and that's why we are getting the first tantalizing hints. And in the future, we will be probing this thing at 1% accuracy. So tracking background expansion to see if lambda is not enough, this you have to see. This I already showed. Let's go to the next one. So let's look at this figure that Anjan said showed again. Come back to this figure. So this is from Planck, and Planck with lensing and BAO that they had. And as you can see, this is a completely flat universe, and this is the degeneracy between omega matter and omega dark energy. And if our Planck Hubble constant measurement, which is 66.93, if that is over here, then we end up with a region where we have a dark energy amount, which is around 70%. So you have to remember that however, whatever the Planck measures for the Hubble constant 80, that feeds into the value of dark energy that Planck thinks. In fact, we can do the same thing with the Linder parameterization of W0 and WA. And this is a scatter plot. And this is the lambda CTM model, which is inside the 1 sigma region in Planck. But if you can look at the value of Planck best fits constant, which is somewhere around here, this is what it is. But now remember, we have this HST80 measurement, which is very convincingly, even with this time delay measurement for lensing, gives you a value which is 73. So this is over here. If this is over here, then the red points will come over here. So look at this. Over here, there are a few red points. These are red points, but if you push it over here, it moves to over here. And yes, exactly. So this is very important. So if you put in, and these experiments, these results are very, very accurate now. So these are trustworthy results. So we cannot just completely ignore it. So if we have this kind of Hubble constant, then we are going into region which is away from the lambda CTM point. Now, Anjan talked a lot about the holy ohm, where you don't care about the omega matter, but he also mentioned that when he does it, he gets omega matter, which is very small, slightly smaller dimension than the Planck value. This is exactly a slightly small omega matter is akin to a high H. So if a slightly small omega matter, as you can see, will push things over here, okay? So that basically means it will push things over here, and this red curve will go up. So this red data points are over here. So it's doing the same thing in a different way. It's a different language, but you are basically going to the same way. You have to either push your omega matter low or push your Hubble constant high. I think it comes to 0.24 or something. Omega matter is quite well. In fact, of all the parameters, omega matter has the highest error bar in Planck. But error bar in Planck. Let's talk about that later. We'll have 5-6 minutes. But the reason is that it's rather, why should we suspect the other 80 more? For a long time, people have been saying that, oh, these 80s are, the suspect because there is this calibration problem. But now, the present 80 measurements, they have nailed down the calibration problem very, very accurate. So 1% calibration error. Okay. And now we have 2 probes, which individually themselves give the same kind of thing. So all the nearby probes gives a high. There's no reason to just completely say that we are going to ignore them, because Planck with this great thing has come. So if we just go to 5-6 minutes, I'll quickly try to do. So even before this thing, the post-Planck results, when the Planck results came out, the data came out, had hints that there may be hints that things are moving slightly away from the lambda CTM, but at very little level. So this is what we did with the Planck data before Planck actually came up with their inflation, with their dark energy paper. And as you can see, the interesting thing is that if you take just the CMB, nothing, no large-scale structure, so no other, Planck, of course, doesn't take growth of structures in their papers, but the other expansion history probes, which is supernova and baryons, you don't take that, then you have the best fitting model of dark energy, which is not a lambda CTM model. It goes in a bad direction, so people would not like it. As soon as you put in your CMB, with the CMB, your supernova and BAO priors, you go bang into your Lambda CDM. And this happens over here. This happens in a different model over here also. So this is something that we did a year before Planck came up with their official results, and they give the same results. So if you have the CMB with BAO, they are very much in Lambda CDM. Just CMB, they are away. In fact, this is what Planck gives, which is what Anjan also showed, that Planck by itself, so CMB by itself is over here, CMB and Wigglez-Baryon is over here, but as soon as you add the Baryon acoustic oscillations and supernova, it goes into Lambda CDM, and this is exactly what we have found a year before Planck came up. I mean, I would appreciate if the Planck would have acknowledged this paper, which large collaborations do not. This came a year before Planck. And this is what Anjan also showed with the parameterization. It goes away from Lambda CDM. If you do not have a parameterization, if you have a model, actually a particular model, even then it goes away from Lambda CDM. Just with CMB. Okay. So let's see if you have looked at the expansion and there is hints, what happens if we add growth to it? So does growth have also hints to it? To see whether Lambda is not enough. So let's go back to this plot again. So over here, this is Planck, okay, with CMB and Baryon acoustic oscillations and Hubble constant. And now, this is where the same thing, so this is Planck, But now, if you look at just low redshift, large-scale structured data, and this is from Wigglez-Baryon of the kids survey, then this is it, this black one. So as you can see, if you do not have CMB, you just have Wigglez-Baryon, another of the probes, the growth of structure probes, which is nearby, where the dark energy should be more influential, it is not consistent with the Lambda CDM even at 2 sigma. So it is more than 2 sigma away from Lambda CDM. And if you look at Planck, then it is. So it looks like there is this hint that if you have an evolution probe that prefers Lambda CDM, if you have a growth of structure probe, there are hints that it may be away from Lambda CDM. Again, this is a figure that Anjan showed, but it's good to go back again, and I'm going to talk a little bit more on this. This is another way of saying it. This is the sigma 8 omega matter plot that comes out of Planck and is associated BAO and supernova. It's a very good thing. And sigma 8 basically is sort of a mass variance, is given by this. One can do the same thing with the Wigglez-Baryon, and this is over here, and there's this tension. Now one can try to see whether this tension, and if you can, there's a way of going beyond the 6 basic parameter model to go beyond this tension. So the first thing you can do is that, okay, neutrinos are there, why don't we put in neutrinos as the 1 plus parameter and see if this tension goes away? So you can do that. You can add neutrinos to the CMB, and you can add neutrinos to the Wigglez-Baryon. As you can see, the tension doesn't go away. The contours move, but the contours do not go inside. So it becomes actually two separate. So neutrinos do not help. Neutrinos, which changes the expansion history, changes the formation of structures, that do not help. What about the curvature? Curvature was fixed in this Lambda CDM model. If we expand on that, let the curvature not be fixed, it becomes worse. So if the curvature is allowed to be the 7th parameter, these two become even separate. So what do we do? Can we have a dark energy where the W is not fixed? So remember, the Lambda CDM model, the W is fixed to -1. Can we vary W? So as soon as we have a varying W model, as you can see, this moves inside and it agrees. So the low scale, low redshift, Wigglez-Baryon, and CMB and supernova, so the growth of structure probe and the expansion probe both agree when you put in a W. Then one can go into trying and physics. This is just a simple W parameters, it's constant W. Okay. And as you can see, this is where the W is. This is what we actually had predicted before. So it goes into this phantom region, which is not very People are not happy, but this is what it is. This is what the data tells us. One can also, instead of having a constant W, have a varying W. So let's say the dark energy actually changes, so go one step. That would also agree. So it looks like that if you want to agree your large-scale structured data, a very precise large-scale structured data now, with the very precise CMB data, then you'd want the universe to behave differently at this late times, at the small redshifts, where having a non-lambda term or non-lambda dark energy is better, makes things agreeable. It's a weak lensing survey. Yeah, it's a latest survey. It's a very good error control. And yeah. Now, one of the things that people may complain that, okay, all these things about having dark energy, other than lambda, comes in if we add different probes. So maybe there is something which you do not know in adding these probes. However, there is hints within CMB itself. So in the CMB, instead of adding probes, what we can do is that we can look at this lensing that we talked about in the kids. This is optical lensing, but we can talk about CMB lensing. Remember, the CMB photons are coming to us through the same matter which lenses the background galaxies. So the CMB photons, the spots, are themselves lensed. So what we are actually getting in the CMB probing is basically the lensed CMB that is coming to us. And so there's a way to delens this CMB and from there find out what is the power spectrum of the matter in between us and the large scattering surface. So one can do that. So it's a CMB lensing. One can do that, and one can sort of come with a formalism like this, where basically the lambda CDM CL will be related to a non-lambda CDM CL with some parameter, and if we get the parameter from the data to be 1, then it's lambda CDM. Planck does the CMB lensing, and within Planck, this AL is 1.22. So it's 2 sigma away from lambda CDM. This is from CMB only. Why does it come? If you look at the Planck lambda CDM data, fit and the data, this comes from these large-scale structures, which is as low multiples, high multiple moments, so small scales, where the lensing happens. So again, it is the lensing, it is the behavior of the universe at late times that has modified things away from lambda. Well, this is where we stand. So, yes. No, it doesn't need knowledge. It looks at the tri-spectrum, so there's a way of doing it, yeah. So it goes to the higher order moment, and from the higher order, so from the 3-point correlation, it goes. So of course, we cannot just stop over here saying that, okay, these are the hints. As you know, this is very tantalizing, and we'll have a long way to go, and without convincing data, as I said, data will lead the way. And so there are many surveys, which is basically now or upcoming, which is going to be looking at this problem of dark energy. Some of them have started and doing right now. DES has come up with results. EBOS is coming. The first results from the Subaru telescope is out. HEDDEX is there. DESI is fantastic. DESI is going to be there, the next big survey, which will be there in a few years' time. And then, of course, we have these really 3 big surveys coming out, which is the LSST Euclid W first. And around this time, the SK will also be coming. Okay. So this is where we stand. So to end, I will just make this comment that dark energy is safe in spite of recent threats, which was there a year back saying that, well, we have not really discovered dark energy. It turns out we have. This is where it is. And if we want to come to this region in the parameter space, we'll have to live in an empty universe. We do not live in an empty universe, so we shouldn't even look at this plot and say that we have not discovered dark energy. We do have dark energy, and dark energy is quite safe. And we know that it is there, but we don't have a clue what it is. Lambda CDM fits very well, but there is very tantalizing hits. There is physics beyond lambda CDM. And there are many ongoing efforts trying to get it, because we have to get things at 1% accuracy, these probes, few percent accuracy. So have patience and keep trying. And so keep your camera. Yes.
Yeah. There is somebody giving the mics.
Ask about one slide when you say that energy wasn't threat. You meant this work by Subir? Okay.
Okay. Any more questions? There were some that were interrupting you within the talk itself. So